Okay, so we have seen the basic procedure of the decision tree. So let's see what are the issues to be addressed over here so that the decision tree works well. First is the missing data. Okay, so it's very difficult if there is some data which is missing. So if you find that there is some missing data, then you need to see that you take care of that missing data. Okay, so what you need to see basically is that can you fill in the missing data with something, or leave out um, the instances which have missing data. Okay. So if you have missing data, the decision tree won't really work well, right. So you won't be able to go along a certain branch, etc., because some particular data is missing. The second one is what is called the multi-valued attributes. So when an attribute has many possible values, so for example, suppose you have like a continuous value. Okay, so your output can take a continuous value. Then how do you divide this into output outcomes, right? So what you need to do is you need to take it and divide it into intervals. Okay, so you'll have to say if it falls between this value and this value, it will go along one of the output branches. If it falls between this value and this value, it will go into another branch, etc. So what you need to do basically is find out where exactly you are going to split this data, and say that they come on separate output branches. So this is something which requires to be done basically. Yeah, another is you can have integer valued or continuous. So again, where are you going to split this, right? And suppose your output is continuous. So what you need is not a classification tree but a regression tree. So a regression tree has at each leaf a linear function of some subset of numerical attributes rather than a single value, right. So you have a numerical function which you are going to use at the leaf. So these are things which need to be taken care of to make the decision tree much more useful basically. So a decision tree should be able to handle all these problems. Handling continuous valued variables is important because in many places you find continuous valued variables, especially in financial problems, etc. Okay. So what they have done is you find lot of decision tree packages which are available, and they have taken care of all these things. Okay. Because decision tree is very popular and it has been used quite a lot. So all these properties have to be taken care of. So one thing about decision trees is one of the best things is that you can easily understand what the reasoning is. Okay, so explanation of why it has chosen a certain class is very easily available. Okay, so an explanation is absolutely necessary. So it's a legal requirement in many cases, especially when it comes to medical field, etc. You find that it is a legal requirement, and because of that the decision tree is very popular because of its explainability and how it is so easy to understand why exactly it is choosing a certain option. So these are some packages which are available, ID3, C 4.5. So these are very well known packages, and then you have things like Slick, Sprint, etc. So let us look summarize only the decision tree, what is happening. So, in the decision tree, what are the advantages? It is inexpensive to construct, right, and it is fast at classifying an unknown pattern, because all you need to do is go down one path in the tree, right. So, it is fast, classification is fast, and it is easy to interpret, that means explainability is there, the accuracy is good, and it can handle categorical as well as numerical attributes. This is also a very important aspect, because most of the classifiers we see do not handle the categorical aspect, especially if you see something like SVMs, or if you see something like the nearest neighbor algorithm, they handle only numerical attributes. Taking care of categorical attributes in such cases is very difficult, because you need to find distance between points. So, something like how similar is this point to this point, and doing that with the categorical attributes is very difficult, unless somehow you can convert those categorical attributes into numerical attributes. For example, if you have something like large, medium, small or something, maybe you can convert it and say large will be 3, medium will be 2 and small will be 1, etc. So, it is possible in some cases to convert it into numerical attributes, but it is not always the case. And what are some of the disadvantages? The training time can be high. Okay, so, the training time or the design time, like we said, it will take some time to build, and it can suffer from overfitting or underfitting, and the tree can become very large, especially if your number of features is very large, right. Suppose you have something like 200 features or more than that, like your decision tree is going to be really large, because number of features are large. So, you need to consider all the features, and it is able to handle rectangular regions, that is the axis parallel split, but the oblique split is the solution, but it makes it little more complex, and it is more difficult to find what is the oblique split that you got to use in a particular case. Okay, so we will now talk about the ensemble learning or the combination of classifiers. So, suppose we combine different classifiers and get the results of combining these classifiers, then how does this actually work? So, let us say you have a particular problem. One method could be that you use something like nearest neighbor classifier, you use a decision tree, you use a rule based system, etc., right, and you're sending in the data into all these three, right. I mean, you have the data. So, suppose you're giving one test pattern, say P, to all these three, right, and you're going to get the class label here, okay, say class 1, this may be giving some class, etc. So, what you need now is actually a decision to be made. Okay, so, let us say we will put one diamond here, you're putting all these values into this, and you have to decide which class this belongs to, right. So, one way could be to take the majority vote. So, you see which is the class which occurs more in this output. So, in this case you have 2 of class 1, 1 of class 2. So, you take your output as belonging to class 1. Okay. So, that is one method. There are other methods of combining it. So, let us see what are these methods we have here. So, you need to combine the predictions. So, that is what we have done here basically. So, what you can do basically is you can generate by cross validation. In other words, you take the input to your decision tree, keep changing it, right. You take a different training subsets, you change the training subsets and put different training subsets and get different decision trees. And then for a new example, you see what are the class labels you are going to get. So, suppose you have an ensemble of 5 hypotheses. Okay, so what you are doing is that you have 5 classifiers, okay, which you are going to use, or they may be all the same classifiers, but you may be taking different subsets of the training data that you are using. And for the ensemble to misclassify a new example, at least 3 of the 5 hypotheses have to misclassify it, right. So, obviously, that is much better than and it is less likely than a misclassification by a single hypothesis. Okay. So, because of that you get much better result when you use the ensemble learning. Okay. So, what happens if a simple calculation shows that using an ensemble of 5 hypotheses reduces an error rate of 1 in 10 down to an error rate of 1 in 100. In other words, it goes from 0.1% to 0.01 or from 10% to 1%. Okay, so, it comes down from 10% to 1%. So, suppose you have your class, positive class to be something like this, right. So, this one with a single hypothesis like this, what this says is that anything to the right of this line will be positive, to the left will be negative, and this one says that to the left it is positive, to the right it is negative, and this one to the bottom it is negative, to the top it is positive. So, if this is your region, what happens is with a single hypothesis it will be difficult to classify this. Okay. But if you have 3 different hypotheses which you are combining together, okay, it may be easier to actually classify this. So, this is a vague way of seeing what are the advantages of using ensemble classifiers basically. Okay. So, you are actually enlarging the hypothesis space. So, if you think of the ensemble itself as a hypothesis and the new hypothesis space as the set of all possible ensembles that are constructible from the hypothesis. So, this figure shows how it can result in a more expressive hypothesis space. So, one method of ensemble is what is called boosting. So, what does this boosting actually do? So, what you can do is that you have all the examples in your training set. So, maybe example x1, x2, x3 etc. Each of these will be associated with a weight, okay, so a weight which is greater than or equal to 0. So, you can start off by saying that all the training examples have a weight of 1, and then as you go on you can change the weight that is associated with each of these hypotheses. So, it starts with Wj equal to 1. So, you take 1 as the value. So, when it uses the first hypothesis, okay, the hypothesis will classify some of the training examples correctly and some incorrectly. Then what you do for the next hypothesis is that the ones which have been misclassified, you decrease their weights. Okay. So, when you decrease the weights, you are decreasing the weightage which is being given to the patterns which are misclassified basically. And then you keep doing for the next hypothesis, for the next hypothesis, etc. And for each hypothesis you are changing the weight which you are basically using, and this is what is called the AdaBoost algorithm, which is a very well known algorithm of boosting, right. So, here we have the AdaBoost algorithm. So, you can see that the weights are being changed, right. If this is equal to yj, okay. In other words, if it is classified correctly, okay, then you do this, otherwise you do this. Okay. So, what you are basically doing is that you are reducing the weights of those which are classified wrong. Okay. Algorithms generates hypothesis by successively re-weighting the training examples. The function weighted majority here, return weighted majority. So, you are returning the weights, generates a hypothesis that returns the output value with the highest vote from the hypothesis in H, with votes weighted by Z. Okay. So, that is the basic idea which you are doing in the AdaBoost. Okay. So, AdaBoost, if the input learning algorithm L is a weak learning algorithm. So, each of them is a weak learning algorithm which you are using, which means that L always returns a hypothesis with accuracy on the training set that is slightly better than random guessing. Okay. So, this is the AdaBoost algorithm basically. So, here we can see that this is how the boosting works. So, if you take these shaded triangles, they correspond to shaded rectangles, they correspond to one example. Okay. So, if you take one example, this is if you take the tick, okay, it shows whether the example has been classified correctly or not classified correctly. And whenever it is classified correctly, you find that the weight increases. Okay. So, the length of this shows the weight which is there for that particular weight. Okay. And then finally, after all this, you will find the final weight here after going through all these. So, when you get a new example, it is classified by taking all those into account, and then you will get one hypothesis H, which is what is being used basically. Okay. So, let us say what are the different methods which you can use to construct your ensemble. Obviously, you want some variation so that you get different hypotheses being created. So, one is actually by subsampling the training example. So, if you use a separate subsample each time, you will find that you are going to get a different classifier or a different hypothesis which you are using. So, one is what is called the bagging. On each run, it presents a classifier with a training set that consists of m out of the n training examples, and that training set is called a bootstrap replicate of the original training set, and the technique is called bootstrap aggregation. So, you take about 2/3 of the original training data, and what you are doing is when you take a pattern, you are not removing it from your data set. So, it is possible it may come again. Okay. So, you can also have some patterns appearing several times also. And another bagging is one, another one is leave out disjoint subsets. So, you divide it into a number of subsets and you take a combination of some of these subsets, leaving out some subsets each time. Okay. So, you drop one subset at a time and you will get a different data set basically. The second method is manipulating the input features. So, what you can do is you can take a subset of the features. So, suppose you have D features F1, F2 up to Fd. You can say that you will take maybe 2/3 of the features and leave out the rest of the features. So, each time you use it, you use different features. So, when you use different features, you get different hypotheses basically. Third one is manipulating the output targets. This is called error correcting output codes. So, what you do is if you have say a large number of classes, the classes are partitioned into two subsets, right. The input data is then relabeled, so that any of the patterns whose class is in set A1 is given the derived label 0, and that is whatever is in B1 are given derived label 1. This relabeled data is given to the classifier, which constructs a classifier H1. So, by taking different partitions A1, A2, you can get different classifiers, and then you can get H2, H3, etc. So, this is by manipulating the classes that you are using. Okay. You divide it into subclasses and change the labeling of the classes basically. And another method which you can use is by injecting the randomness. Okay. It generates different classifiers by injecting randomness into the learning algorithm. That is, the order in which features are chosen to make a decision at the internal node can be chosen randomly out of the top best S. Okay. In other words, you do not use the best attribute always, you can randomly change it. You use one of the better attributes, but you can change it and that will change the entire decision tree, right. So, you can get different decision trees which gives different hypotheses basically. Okay, now we need to see what are the methods for combining these classifiers. So, once you get the class labels as the output, how do you combine these? Okay, the simplest and most robust approach is to take the unweighted vote, in other words the majority vote, like we said. A refinement on this is when each class can produce class probability estimates, okay, rather than a simple classification decision. So, you get P of some class some pattern x is equal to C, okay, f of x is equal to C, in other words that it belongs to C given some particular hypothesis. Okay. So, these are the values that you will have, okay, and you will have this for every class C. Okay. So, you will have the value for a pattern x, you will have this value for every class C, right. We can combine the class probabilities of all the hypotheses, so that the class probability of the ensemble is. So, what you do is you will have this for H1, H2, H3, okay, all the up to HL. For every hypothesis, you will have this probability for every class. Okay. So, for a particular class, what you do is probability that it belongs to class C will be combining all these values that you have and taking an average of that. Okay. And you can do this for every class C. So, for 1 to capital C, every class C you find this value and then the predicted class will be the class having the highest class probability out of these. Okay. So, that is how you combine these things. Okay, so that is about ensemble classifiers. So, we will stop this session here and continue the next session.